Okay, are we ready? If a covalent structure has more than 5 atoms, I will lay out the atoms for you, but you will have to fill in the bonds and lone pairs. For example, so greater than 5 atoms in a Lewis structure. Because if I give you, for example, CCl4, that's 5 atoms, and you'll put the carbon in the center and the chlorines around it. That you should know. However, if I give you something like this, I would not expect you to know that you put the carbon and the oxygen in this arrangement. However, I will say fill in the bonds and lone pairs on this Lewis structure. So what is the, and it's always going to be covalent. I'm not going to do this for ionics. It's always going to be covalent. So what is the first thing you do with a covalent Lewis structure? You have to count something. Valence electrons. How many valence electrons do I have here? It's 14. You have 4 times 1 for the hydrogens, plus 4 for the carbon, plus 6 for the oxygen, which gives you 14 valence electrons. Does everyone see how I did that? Where do I put the first electrons? In the bonds, right? So I'm going to put 2 between each pair of of atoms. How many valence electrons have I used up? Good. Where I have 4 left, where do I put the 4 other valence electrons? Around the oxygen. Why do I put it around the oxygen? It's the only one that's not happy. Each of the hydrogens has 2. Hydrogen can only have 2. It can only have a single bond and no electron pairs. Carbon is totally happy. It has its 4 bonds. Oxygen is like, I only have 2 bonds. I want 4 more electrons. You put them right there. Okay? And then the last step is that you would get rid of these and you would just draw. So this is what you would draw at the end. So it would be, I would have the atoms laid out for you, and then you would just fill in the bonds and the valence electrons. Any questions on the lone pairs? Any questions on that? Please do. That. That's one. Someone's not happy.
I'm not happy.
What are the atoms?
What are the atoms?
One of your atoms. All right. How many valence electrons do we have? 18. Why? 4 hydrogens, so 4 times 1 plus 2 carbons, so that's 2 times 4 plus 1 oxygen, which is how many valence? 6. That should give you 18 valence electrons. Fantastic. Let's start putting in our pairs. 2, 4, 6, 8, 10, 12, 14, 16, 18. Are we good? No, why aren't we good?
Oh, because carbon's not happy.
Carbon only has 6 electrons. So who's going to help out carbon? Oxygen. Oxygen is going to throw one of its electron pairs into a double bond. So you're going to end up having 2 there. How are we feeling now? Everyone's awesome. So the last step is just to erase those lone pairs and draw in your. Any questions on that? Remember how we talked about how many bonds does carbon like to have? 4, because it's missing 4 valence electrons. It likes to have 4 bonds to round out its octet, and you'll see that both of these carbons have 4 bonds. How about oxygen? How many bonds does oxygen like to have? 2. It does have 2. It has a double bond. It's happy. Questions? Concerns? It should help you. You know, you should be able to figure it out from the valence electrons and making everyone's octet good. But if you have a carbon that in diatomics it's a little different because like for example carbon monoxide has a triple bond between the carbon and the oxygen just because there are so few electrons. However, if it's a larger molecule and you end up with a carbon with 3 bonds, it's likely that something's amiss. Okay. It's just a way to check it's another method to check your structures. Everyone get your electronegativity chart out. Anyone not have them? Okay, I have only 2 extras. Can you go make copies?
Yeah.
There's 2 of you. Everyone else for now share. How many do we need? Can you raise your hand again? 1, 2, 3, 4, 5, 6, 7, 6, 7. All right. Polarity is the difference in electronegativity between two bonded atoms. Remind me what electronegativity is? Tendency to pull electrons towards itself, otherwise known as, I like to say, greediness for electrons, how much it wants electrons. So this doesn't always mean that the it's gonna be like an ion where it's gonna take an electron. Sometimes it's gonna share an electron but kind of pull it towards itself a little. And we know this by our delta En. So our difference in electronegativity is delta En. That's a triangle. Looks like a Hershey's Kiss, but it's a triangle. And that is equal to the absolute value of the electronegativity of atom A minus the electronegativity of atom B. So our number will always be, it's an absolute value? Positive. It will always be a positive number. For a CH bond, what is the electronegativity of carbon? Look at your electronegativity charts. 2.5. How about hydrogen? 2.1. My absolute value of that difference is 0.4. That's my delta En. For CCl, 2.5. What's chlorine? Anyone tell me? 3.0. So even though this number is bigger than this number, it's still the absolute value. So our answer will be 0.5 positive. That's for delta En for a carbon-chlorine bond. We have what's called a bond polarity scale, which tells us, based on the difference in electronegativity between two atoms, what type of bond that is. I'm going to go on to the next screen. I'll give you a few extra seconds to write this down. We have a bond polarity scale, which I'll write on the next screen, and it tells you what type of bond you have based on the difference in electronegativity, based on the delta En. All right, can I? Yes, Jacob. No. This has no units. You don't have to. You can, yeah, you can write delta En equals, but this actually requires no units because it's a scale. So it actually doesn't have any units, but that's an excellent question. Just make it clear that you found the delta En, box it or something. Bond polarity scale, which will be given to you on the test. If your delta En is less than or equal to 0.4, you have a nonpolar covalent bond. And I will talk to you about what a nonpolar covalent bond actually means. But if you have a delta En that's greater than 0.4, but less than or equal to 1.9, it is a polar covalent bond. And if we have a delta En that's greater than 1.9, it's an ionic bond. So we actually have another way to classify anionic bond, and we'll prove in a few minutes that the difference between most metals and nonmetals will give you this delta En. So it's just another classification of an ionic bond. Yeah.
Why is this like relevant? Why is it relevant? But like, why are we looking at this to see like how reactive it's gonna be?
This, yeah, raise your hand if you need an electronegative feature. That's a really good question. We're going to talk to you about intermolecular forces later on in the class, but polar bonds and molecules play an incredibly important role, especially, I mean, like really in any chemistry, but especially in biology and marine science and things like that. You will use this. And because not only are there bonds within molecules, but there's bonds between molecules, and those bonds between molecules affect how liquids act, solids act, where your boiling point is, where your freezing point is, things like that. It's another characteristic of the molecule that determines how it acts. The question?
I'm going to point out that you learn later in other chemistry courses that like solvents and solutes with polar bonds react together, and that they're not polar, they usually don't.
Exactly. Like oil and water. Water is very polar, oil is non-polar. And we'll dive into that a little today. But yeah, in 110, it will come back. And so I'm just introducing it now. But in 110, and I mean, Henrik Piebach, who teaches Bio 210, is like, they have to know electronegativity, they have to know polarity, because he talks about it in terms of the molecular interactions in your body all the time. Yeah. What is the delta En for a carbon-carbon bond? 0. Any bond that is between two the same atoms will be 0, because it's, for example, for carbon-carbon, it's 2.5 minus 2.5, which gives you 0. So that's a what type of bond? Non-polar covalent. How about a CO bond? We know that carbon is 2.5. What is oxygen? 3.5. Which gives us 1.0. What type of bond is that? Polar covalent. What's Na? Yeah, but like what's the electronegativity? 0.9. And we already know that chlorine is 3.0. That gives us 2.1. So what type of compound, what type of bond is that? Ionic, which we already know, but we're just confirming it with this scale. So what do these bonds really look like? We draw Lewis structures, and we have our electrons in nice little pairs. There are many, many ways to draw bonds in atoms, and Lewis structures is one way. I'm going to give you another way, which kind of better illustrates polar versus nonpolar versus ionic bonds. If you have a nonpolar bond, for example, O2, all molecules have an electron cloud. And because even though in Lewis structures we draw these, electron pairs, electrons are constantly moving around their atoms. And because they're not always in the same place, we kind of call it an electron cloud, the general area of where electrons belong in a molecule. And we draw it as kind of a shape around the molecule. In a nonpolar bond, the electron cloud is evenly distributed between both atoms. Okay, so the electrons aren't favoring either atom because you don't have a big enough difference in electronegativity. One atom is not pulling on the electrons more than another. However, that's a covalent. And if you have a polar covalent, like carbon monoxide, which atom is going to attract the electrons slightly more? It would actually be oxygen, because oxygen is more electronegative. It's more attractive to the electrons. So your electron cloud is going to look more like this. The electrons are going to be floating around both atoms, but a little more around the oxygen because they favor being around the oxygen. Oxygen is more electronegative. It pulls them towards itself. Does everybody see that? Look the same. No, it's fine. Let me exaggerate that a little more.
I'll exaggerate on my examples too.
How's that?
Great.
Okay. With an ionic, the difference is so big in terms of electronegativity that one atom has given up an electron and the other atom has taken up an electron. So in this case, for example, Na plus and Cl minus. Let me draw that a little better. They don't have the same electron cloud, but one is positive and one is negative, so they kind of are drawn to each other because one is slightly more negative and one is actually negative and one is positive. Does everybody see the difference? It's kind of a progression, right? So you have equal sharing, you have one that wants it a little more and one where they're not willing to share at all. Okay? Elliot. Mm-hmm. It like the C-C is like the carbon-carbon bond. And then the math 2.5 minus 2.5, that's subtraction. Yeah. So when we have a polar bond, you can draw a polarity arrow on or near the molecule. So I'm going to take away this and this. Carbon monoxide is a polar bond, which means if I ask you to draw a polarity arrow, the arrow is going to point towards the more electronegative atom, which is oxygen. So your arrow is going to look like this. A polarity arrow, will show up. Yeah, a polarity arrow is an arrow with a little crossbar on it. I don't care where you draw this arrow in relation to the molecule. If you draw it under, if you draw it over, if it's to the side, as long as it's going in the right direction. And then if I draw this way, where would the arrow be facing? Up. So it doesn't matter which way you draw the molecule. The arrow always has to point in the direction of the more electronegative atom. So I might say, draw the Lewis structure of carbon monoxide and put a polarity arrow if appropriate. And what I mean is, if appropriate is, if it's polar, draw a polarity arrow. And if I said, and then I'd say, if no polarity arrow is appropriate, indicate that. So, for example, with O2, this is a nonpolar molecule. So you would have no polarity arrow, and you would write no polarity arrow or nonpolar or something to give me the idea that you are aware that this is a nonpolar molecule. If you say nothing, I'll assume you forgot about the polarity arrow part. Okay, so you either draw an arrow or you say no arrow or nonpolar. Does everybody understand that? Okay. I would like you to draw, I don't know why I just didn't go to the next page. Oh well. Draw the following compounds. Determine if they are polar. And give me a polarity arrow if appropriate. If not, say nonpolar or no polarity arrow. Draw out the Lewis structures of these compounds as well. Yes, but I want it. This is not the Lewis structure. This is correct. It's not the Lewis structure. So count it down to electrons. first step, drawing a Lewis structure. Count the valence. So you draw out the H and the F. How many valence electrons do we have? How many? 8. Fluorine has 7 valence electrons. Hydrogen has 1. So we have 8 valence electrons. We're going to put in our 2 electrons in the bond. Where do we put the rest of the electrons? Fluorine, because hydrogen can't have any more. And plus, fluorine is in row 7A. It wants 1 bond. It is electronegative. It wants to have as many electrons near itself as possible. So this is what this should look like. Is this a polar, non-polar, or compound? Polar. So which way does our polarity arrow go? Towards fluorine. This way. Excellent. That's all I want. How about N2? How many valence electrons do we have? Because each nitrogen has 5 valence electrons. It's in 5A. Let's put in our 2 there. 2, 4, 6, 8, 10. We have a problem. What's our problem? This nitrogen is super unhappy. So the other nitrogen is going to contribute 2 of its electrons. How are we feeling now? Still not happy. We still only have 6 electrons here. So we're going to have to donate 2 more from the other nitrogen, which is what? What is that? Oh, I accidentally got rid of the nitrogen. There we go. It's a triple bond. Is this polar, non-polar, ionic? That is not how you spell non-polar, but never mind. Non-polar. Questions? All right. Let's talk about intermolecular forces. Can anyone tell me what intermolecular forces means? It's actually not inside. That would be intra. Think about international relations. Interpersonal relationships. Between. Okay? So we're talking about 2 molecules interacting with each other. So it's the bonds not within molecules, but between molecules. And the reason that polarity really matters in terms of intermolecular forces is because we have this thing called a dipole. I'm going to use my friend carbon monoxide again. And remind me where most of the electrons are going to be. Where's the cloud going to be? Near the oxygen. Okay, so we're going to do, is that better? So which end is going to be more negative? Oxygen. Because more of the electrons are going to be on this side. So we draw this little thing that's called a delta negative. It's like a D with a little hook on the top, or an S that kind of curls around itself. It's in lowercase delta. Delta negative. And then our delta positive is going to go near the carbon. So any polar molecule has a dipole. This is your dipole. The fact that one end is almost always a little more negative and one end is a little more positive. They're not charge states on these atoms because these atoms are still sharing electrons. It's still a molecule, but just one end of the molecule is just a little more negative. The other is a little more positive. So polar molecules have dipoles. O2, does that have a dipole? Is one end more positive or negative than the other? No. Nonpolar molecules have no dipole. Or at least not a permanent dipole. It's not always positive and negative, or positive and negative on one side. Yes. This one side is a little more negative than the other. It's just, it's like a magnet has a dipole, right? A magnet is a dipole. One end is negative and one end is positive. And based on which, and if you have two magnets, if they have dipoles, which way are they going to arrange in relation to each other? Are the positive ends gonna attract each other? No. The negative end is going to be attracted to the positive end of the other dipole. And that is how molecules work with dipoles. They're like little magnets. One end is a little more negative, one end is a little more positive. So they're going to interact in a way to align the negative end with the positive end of the other molecule. I'm going to talk about 3 different types of intermolecular forces. The first is the weakest, London dispersion. For these intermolecular forces, London dispersion. It's not after the city, it's actually a guy named London. London dispersion forces, you have to know the order, weakest to strongest of these forces, and you also have to know what type of molecules they form between, okay? London dispersion forces happen when there are between molecules that have no dipoles. So what type of molecules are those? What type of bonds? No dipoles? Non-polar. Non-polar molecules. Without going too deeply into this, non-polar molecules don't have permanent dipoles, but they do have electron clouds that sometimes fluctuate slightly. And sometimes if 2 molecules approach each other, one might instantaneously have a positive end, slightly positive end, one might instantaneously have a negative end, and they'll kind of stick together a little bit. But not like they would have, not like molecules with dipoles would be. So these are just kind of chance encounters where the molecules are instantaneously attracted to each other just for like a fleeting moment of time. Dipole-dipole interactions. Based on the name, what type of molecules do you think form these type of interactions? Polar molecules, because polar molecules have dipoles. These are stronger because polar molecules always have a positive and a negative end, and they're going to attract the positive and negative ends of other molecules. So if you have carbon monoxide, once again, the oxygen end is going to be a little more negative, and the carbon end is going to be a little more positive. So this positive is going to be attracted to this negative, and so on down the line. Just like if you lined up magnets, you would have one end positive and the next negative, positive, negative, so that they attract each other. And this is how polar molecules interact. They attract. Because one end is slightly positive, and then the next one will align with its negative end. Any questions on this? The final IMF, intermolecular force, that I'm going to talk about is hydrogen bonding. This is the strongest. And it is basically a stronger dipole-dipole interaction. And it happens between molecules. Actually, I'm going to go on to the next page with this one because I want to draw. Does everybody have this down? Can I move on? Okay. So hydrogen bonding. Which is the strongest. Happens between molecules with OH, NH, and FH bonds. And these are just stronger dipole. So it's a special kind. What molecule can you think of that would be really good at hydrogen bonding? Water. Water is only hydrogen bonds. It's only OH bonds. So water, the reason water has such a high boiling point for its size, most molecules that are only 3 atoms have a lower boiling point than water. But water is really good at sticking together because it has these really strong intermolecular forces called hydrogen bonds. Water is going to line itself like this. Which end is the positive end? The hydrogen. Which end is the negative end? Oxygen. So in solution, as a liquid, water is going to form this lattice where the oxygen is going to be next to a hydrogen, which is going to be next to another oxygen, et cetera, et cetera, et cetera. Any questions on this? I might say, when you draw a diamond, I might say, would this molecule form hydrogen bonds? And you would say yes or no. Or give me an example of a molecule that forms London dispersion, that only has London dispersion forces, things like that. Those are the kind of questions I will ask. You don't have to draw this out. You will in 110, but this is kind of just a brief introduction to intermolecular forces, which you will keep learning about, and you realize that it has to do with vapor pressure, boiling point, freezing point, all of those things have to do with intermolecular forces. Questions on that?
Would you say the more electronegative something is, the more negative it's going to be?
Not necessarily. What about a Cl-Cl bond? Exactly. So the difference in electronegativity matters more in polarity than the electronegativity of individual elements. individual atoms, right? Because if you have a Cl and a C, yes, then that Cl is going to be very negative compared to carbon. However, if you have two Cls, like in Cl2, the Cls are going to be sharing those electrons equally, so neither end is going to be negative. So the delta En, the difference in electronegativity, is very important. Okay? That's all I have for today. So you get to go a little early.